Okay. Okay, folks. So welcome to Lecture 16 of ECE3311, Principles of Communication Systems. Today's lecture, we're going to be continuing yet another different type of analog modulation scheme, double sideband suppressed carrier, or DSB-SC. Okay. We'll also look at a couple of techniques used in order to synchronize against DSB-SC, okay, which is the Costas loop and the squaring loop, which is kind of somewhat similar to that of the phase lock loop that we talked about before. And actually, no, I am so totally kidding. So Costas loop and squaring loop, so they are structured a little bit differently, and we're going to go through a little bit about how they are implemented, okay? So today's lecture is going to be kind of a smorgasbord of modulation scheme followed by detection scheme using Costas and or squaring, right? So let's jump into this. All right. So we've seen this before many a time, right? So with AM modulation, with PM modulation, and with FM modulation. So how is DSB-SC different than the other three? So it is almost the same as AM modulation. So what I want to do is I want to start off with that, okay? So let's jump into that. All right. So first of all, very important, so general expression. So my passband signal, PB, right? Passband. You take the real, okie dokie, of the mapping of my message signal to some baseband representation, complex baseband, and modulate to some carrier frequency FC. All right? So far, so good. We know that for AM, that mapping is the following, right? So this is kind of interesting. So what we have here, right, is the mapping function is equal to some sort of constant amplitude, okay? We have some DC bias, okay? And that's our message. Okay, great, right? And we saw how in the time domain that behaves. Now, DSB-SC. How does that worky? Okay, so the mapping for this is that, right? So we don't have the bias term. Almost the same as AM, but no DC bias. Okay, so what ends up happening is we almost have the same type of waveform, but like as an AM waveform, right? The complex baseband waveform, baseband because it's not complex, unless AC is complex or MOT is complex. But otherwise, if both are real, you have a real baseband representation. And what effectively we got here, okay, is we have a signal that essentially, if you have, if we go through the same process and get the passband representation, it's going to be the envelope without any DC bias, right? So this, of course, makes things a little bit weird if, let's say, M of t has any negative values because we have that 180 degrees phase ambiguity and makes it very difficult to extract out what the signal should be at the other end, right? So, but DSB-SC, okay, double sideband, okay, suppressed carrier. Okay, so you might say, okay, what does his name mean, right? So what we want to do is let's go through the exercise of comparing the G's, AM and DSB-SC. Okay, so we got here, what do we got? Oh yeah, we got this, boop, boop, boop. And here, it's just that. So now what I would like to do is Fourier transform it. Okay? So what we do is we take the Fourier transform. So what we got is AC plus AC M of t, right? Here, it's the Fourier transform of AC M of t. Okay, and we have an assumption, okay, or aside. No, it's not an aside. This is actually kind of important. Note, okay, that the Fourier transform of M of t is equal to M of f. So what do we have? Well, at this end, okay, the Fourier transform, well, the second part's kind of, so first of all, Fourier transform is a linear operator, so we can apply it to each individual term in the case of the AM case. Awesome. All right. So we got AC M of f. Okay. What about the first term? What is the Fourier transform of a constant? It's a delta. AC delta f. How about here? What is this fella? AC M of f. Okay, cool beans. So now, okay, now this is kind of super important. Okay, so now we have these representations. Awesome. So now what we want to do, okay, so continuing right along. So what we got is we have G of f, right? And G of f is equal to AC delta f plus AC. Not enough coffee this morning. That, right? So remember, this is AM. This is DSC-SC. Okay. Now, what does the general expression say? So in both cases, gen expression. So what does this look like in the frequency domain when I modulate? Well, let's go back. Here we go. So spectrally, again, heads up, S of t, S of f is V of t, V of f. Like S and t, they're the same thing. I just like mentally just went poof. I'm going to change variable on you folks. Same thing. Both are passband signals. So just in case you wonder where the heck V went. But this is actually kind of important. So look at this. The spectrum, right? The spectrum is what? The spectrum here is there's going to be a shifted version of G of f that goes to FC. And there's going to be a complex conjugate version of that that's going to be shifted to minus FC. Right? So let's do this. There we go. So just remember, S of F, which is equal to V of F. So Wyglinski's just reinforcing that. Sorry. There we go. Is equal to half complex conjugate minus F minus FC. Same thing here is equal to that. You could have also derived this if you wanted to. Would come up to exactly the same thing. And what would this look like? This would look like the following. So when in doubt, plot. Okay? What does G of F look like at DC before we modulate? It's going to look like this. So let's say M of F looks like this. Let's say M of F spectrally looks like this, a triangle, but no loss in generality. It could be any shape you want, but let's say we choose M of F to be that. So, and again, this is the magnitude response. There's also a phased response, but I'm not going to spend time trying to derive that, all right? Just for sake of fun, we're only going to look at the magnitude response. So what it's going to look like, so G of F for the AM modulation, it's going to look like this. It's going to be M of F, that shape, multiplied by AC. Oh, and a delta right on top there. AC delta F. Ha ha! Now, double sideband suppressed carrier. It only is this. No delta. Nope. So what happens is when I modulate these things, okay, you get this. So you get minus FC, FC, minus FC, there we go. Minus FC, FC, delta, delta, because of this thing, right? You don't have it on this end. Oh, forgot. Blue. It's all, remember that the G of F waveform is also reduced by a factor of half, right? It's because of this fella here and here. But spectral shape-wise, this is great. Modulate there, modulate there, modulate there, modulate there. So you might say, okay, so what, Wyglinski? Well, this is what, so what? Carrier, right? So it's that delta function that is the difference between AM and DSB-SC, is the fact that I have this delta here, and that delta is not present over yonder, right? So that's the difference between the two, okay? So what ends up happening, that's the difference between DSB-SC and AM, is the lack of that delta function, right? That's good and bad. And you might say, how? Okay, So the reason why this could be good and bad is with AM, it's actually kind of nice to have that delta because then you can establish a lock, right? So imagine you have that radio channel thingy, right? And it's at 530 kilohertz, and you have something, right? And there's noise, so you can't really tell, or maybe it is, but then whoop, you got a little spiky thing. That spiky thing actually helps get you a lock, right? For AM radio, right? So let me see. Let me see if I can quickly pull something. Yeah, ha. There we go. You might say, what the heck is Wyglinski doing and yabbering? Here we go. Let's do it. Let me show you what I'm yabbering about. And still, yeah, it's good to have two computers. Let's share here. There we go. That is AM radio spectrum, right? So jugga, spiky thing in the middle. That spiky thing should be smack dab on FC. So in terms of locking, it's great because you can tell where that signal is precisely. You don't have to do any sort of like figuring out, is it 50-50 or is it a little bit over there, a little bit, like there's no uncertainty where that delta is because it's 1/2 of the magnitude response in terms of height, okay, for that AM transmission, right? So in many ways, that's a really nice feature to have in terms of establishing a lock. Of course, the bad side of things is your dynamic range now is also quite a bit, it's double. So that means that your radio equipment, especially amplifiers and other nonlinear components, need to make sure that you don't do something called clipping. So if you send that voltage signal, it says, well, my dynamic range is beyond what my radio hardware can achieve. I don't begin saturating my radio frequency front end and cut out electromagnetic, the signal. And when you clip a signal, it's bad news. It creates a lot of spurious emissions outside what it's designed to be. Okay, enough of that. I'm going to go back to doodling. All right. All right, so that is the difference, okay, folks, between DSC-SB. All right, so now we got that. We got this expression for DSC. So essentially, for a DSC-SB signal, what do you got? So frequency, whoop, whoop, bloop, no delta. So this is good and bad. Good, because now I can have cheaper hardware because I don't need to have that range. I can have my dynamic range and still be happy. Bad thing is, as you guessed it, so here, lower dynamic range. Okay, but harder to do frequency lock. Okay, so that's where the Costas loop and the squaring loop come in. So enter Costas loop and the squaring loop. Okay. So general expression. Here's your DSB-SC, right? Expressions. And now this is where we're going to talk about the decoding. So there are two ways of doing this, right? So the Costas loop, what you got to do is you have, let's say that's your input, your passband input to your receiver. One trick is to multiply this by a sine wave, and there's also going to be potentially a phase offset. That's what theta E is. And what you do is just like what we've been doing in the past, right? With like envelope detection, it's kind of similar in many ways, in fact. But what happens is we know that if we do this thing where we multiply by another sine wave, we're spot on with respect to carrier frequency, and all we have is a small phase offset, right? We can actually, multiplying by that sine wave with the same frequency, and then using a low pass filter to remove the double frequency term, we can successfully extract out the message signal as is multiplied by the cosine of that phase difference. It's so beautiful. Let's look at this. Okay, let's derive it. Well, actually, even without deriving it. So in Canvas, I actually explain step by step. So in case you look at this post-mortem, right, and you look at it and say, what the heck is Wyglinski talking about? I actually have this. This is uploaded in Canvas, right? So what ends up happening is this fella, okay, goes in, right, into this structure, right? And what happens is you have the following. You have both a sine and a cosine that are multiplying against your SFT, your passband signal, right? So this is going to be cosine times cosine. This is going to be cosine, and what happens is the voltage controlled output cosine wave, it goes under a 90 degrees phase shift, so now it's a sine, okay? And what happens is it's now sine times cosine. So now what we get, right, is we get cosine cosine, and at this here, it's going to be cosine sine, and it's going to also have that phase offset, right? And if you do the trig identity, cosine A, cosine B, what it should be equal to is cosine A plus B, cosine A minus B. So we get this. Here's the double frequency term, and here is just cosine of the phase. The low pass filter removes the double frequency term. So what we're left with is just a cosine E. Sorry, the cosine theta E. At this end, cosine A sine B, what does that produce? Cosine A times sine B, okay, gives us sine A plus B plus sine A minus B, okay? And the low pass filter gets rid of that double frequency term. So what we end up getting there at the output is a sine of the phase difference. Now, what we do is we take the cosine theta E and we take the sine theta E, multiply them together. That's actually the interesting part. We take cosine theta E, sine theta E, multiply them, and again, trig identity, we now get this guy here, which is the square of the message, okay, times half, okay, of sine 2 theta E, okay? So it's 2 times the phase. That's what the trig identity gives us, right? So now we feed that through the low pass filter, okay? And what the low pass filter does is it removes all the high frequency components and only leaves the sine 2 theta E. So, and what's the high frequency components? We make the assumption here that that m of t squared is actually, because of the squaring term and everything, is higher frequency than that of the sine 2 theta e. So what it does is it smooths out that input signal, the m squared t half sine 2 theta e, and what comes out is just the sine 2 theta e, and that is what gets fed into the VCO, and we start all over again with that loop. Okay, so what we get is this kind of like, you know, what happens is this process allows us to create, okay, our sinusoid excitation, right? That does this process with a theta e and helps us establish that lock, okay, with a constant phase difference, okay, and then that is what and frequency, and then that is what gets fed and is used to demodulate our incoming signal, okay, which is m of t cos omega c t. All right. So that's how the Costas loop works. So we take the same signal, we demodulate it using cosine and sine. So we demodulate it into an I and Q, okay? And then we take advantage of the result. So the baseband component of I and the baseband component of Q, which should have the phase term in it. And then we multiply that together, low pass filter it out, and then feed it into the VCO in order to continue the lock, right? So perfect. That is perfect. And we just keep on doing this. All right. So this, okay, this sort of diagram, right, explaining how the Costas loop works, this is available in Canvas. Okay, so check it out in Canvas. It's under, if you go in Files, under Files, and then Miscellaneous, you can download this exact same thing. All right. Now, right, if we go to squaring loop, this too we've seen before, right? And also under Files, Miscellaneous, and I think it's under Loops. So look for under Files, where all the files, PDFs and such for this course is, go into Miscellaneous, and then go into Loops, the directory Loops, you'll find exactly these explanations. All righty? Now, for loops, almost the same thing. Okay? Here, the way loops work, squaring loop works, take your signal, square it, right? You square it, so now you have s squared of t, which means cosine squared of, so what does that give me? Well, so some trig identities to pay attention to. So when we have this, two times two. Okay, and then of course we know right? We also saw and this one I totally forgot. So let us see. I'm already like there we go. These are product identities. Yep. Yeah, that's it. Okay, yeah, that's what I thought. Yep. So these are ones that you're going to see a lot in this class, right? And you've already have, right? And then of course there's sine squared. And this should be equal to yeah, it should be half minus. Because I just want to make sure I don't give you folks a wrong answer. Shucks. Nope. Here we go. Yep, that's correct. All right. So these are the trig identities that come up a lot, right? So going to the squaring loop. So if we have S of t is equal to what? So we know that S of t is going to be AC m of t, right? Cosine 2 pi fc of t. That if we do the square law device, s squared of t, okay, and then we know that this is going to be this plus this cos double contents here. All right. And so we know that the next step in the squaring loop is going to be, let's switch over to it, is going to be a bandpass filter. Okay. So what happens is the trig identity, what we want, okay, at the end of the day, is like if we choose a bandpass filter and the cutoff frequency is 2 times fc of t, what does that look like? So let's just go also to our notes again. So here we go. Okay. So what happens is we apply the square law device, and then the bandpass filter centered. So what we want, we explicitly, so this is totally different than what we've done before, right? How so? Well, remember in previous implementations, we always wanted a DC term. Not here. What we want here is we explicitly want the double frequency term, okay? So in this case, we want, tell me what you want and really, really want. And that's what I want, what I really, really want. I don't want the DC term. I want the double frequency term. Okay. So I have a BPF, bandpass filter. So it's whatever. So if we had like this guy here, okay, and we know in the frequency domain, that's going to be a delta at the origin, and this is going to be something centered at 2 times FC, okay? What we want is we want that thing to, so we want a bandpass filter at 2 FC, and of course, we're going to have, like, it's going to be a bandwidth B, and we want to filter that out and reject everything outside, including the DC term here. So what we'll get at the end of the day is we're going to get AC squared m squared of t, boop, cos 2 pi fc of t. That's what we want. Okay? So then after that, what's the next step? So next step after that is something called a limiter. Okay? So what the limiter does is it will remove, okay? What it's going to do is it's kind of like a low pass filter. It will have the same sort of sort of purpose as a low pass filter, except that we're now at passband frequency. We're at the double frequency term, right? But what the limiter does is it smooths out the signal, which effectively means is that if there was any M of t information, it gets smoothed out. So what we'll end up getting is just the cosine double frequency term. And M of t basically is removed out of our signal. So yeah, so there's this thing. So it goes into the limiter, and its role, the limiter, is remove, smooths out M of t, or M of t squared. So what we get at the end of the day is some constant, A naught, cosine 2 pi fc of t, right? Another way of writing this is A naught cosine 2 pi 2 fc of t. Okay, there's my double frequency term. Now, we have a frequency divider. Okay, so the output here, I'm going to use a different color, will now be A naught cosine 2 pi fc, not 2 fc. And then that, folks, gets multiplied with my original signal. And then from there, I use a low pass filter to extract out M of t. So that's how the squaring loop works. Okay, so the squaring loop explicitly is this. All right, and that's how we get a cosine 2 pi fc of t that then extracts this out like a specific, we apply to that to get M of t. All right, so that is lecture 16 of ECE 3311. What are the learning moments? What is the walk away from this lecture? Well, there's this thing called double sideband, DSB-SC. Okay, which almost looks like AM modulation, but doesn't have the delta, which makes it better and worse. Better because it doesn't have as big a dynamic range. Worse, the problem is harder to lock onto. So therefore, enter squaring loop, enter Costas loop, which we just seen, which are techniques in order to be able to lock onto a DSB-SC signal, which we saw here. So again, so that is, where the heck am I? So that is lecture 16. So definitely in terms of material that would be taught on or asked for in a class test would be things like, for instance, implementing such a thing, perhaps also variants of a DSB-SC type of communication system, where we might have, for instance, you'll need to design. You would need to sort of like design factors of, like, let's say this is the bandwidth of a signal. What's your choice of bandpass filter in terms of the lower and upper cutoff frequencies? Or perhaps I have something where I have multiple messages embedded in the communication system, but I only want to extract out one. What would be the choice of bandpass bandpass filter specifications, and also what carrier frequency I want to select out at the end of the day? What carrier frequency do I want to have? Okay, because of the frequency divider. So with that, that concludes lecture 16.